thank you for your attention at first.
Maybe you say your name, please.
Yeah. It's on? Now?
Okay, perfect.
My name is Ralf Bovanek. I'm from the University of the Federal Arts in Munich. And I'd like to tell you something about thermographic image analysis. In former studies, we found some problems in this kind because of motion, and therefore we try to solve this problem with a motion compensation. And we have no clear attention how login works, so we try to invent our own login algorithm because no one ever said how we does it. First of all, I will show you the experimental details. Second part is explaining how we compensate the motion. Then a short expose to the DFT login method. DFT stands for discrete Fourier transformation. Then show you the results of motion compensation pictures and pictures without motion compensation. And at last, a short conclusion and outlook. This is our testing machine. Our specimen is 4 millimeters width at a width of 4 millimeters, a depth of 4 millimeters, a width of 12 millimeters, and a length of 80 millimeters. It is polished to have a plain surface for better images, and it's black coated for a better emissivity. We can do two kinds of experiments. We can do constant force experiments or experiments with constant stress intensity. For experiments with constant stress intensity, we measure the crack length via potential drop, and this crack length is delivered to this value of the potential drop is delivered to the controls, and they estimate the force. Our thermographic images were recorded with a titanium 560 camera from FLIR with a camera with a frequency of 99 Hertz, and we automatically recorded some pictures in a fixed distance. So we take 990 pictures for 10 seconds and then wait 2 minutes and take the next. So there's no clear connection between the experiment and the camera, but we started both at the same time. So we have fixed grips, so we can do a stress ratio of -1. That's all. And the motion compensation. The first part of the motion compensation is an edge detection algorithm already used by Fedorova et al. In 2012. And based on this algorithm, I developed my motion compensation technique. The result of this edge detection algorithm is an edge picture. We define a threshold of gradient, and if the gradient on the picture is above, you get 1, and the gradient below, you get 0, and so we get a bullish picture of your specimen. Next step is we define 2 alignment zones for cross-correlation, one upper, one lower, and you extract this special pattern from the first picture and look where is this pattern on the following ones, and via the next step, via this cross-correlation, you shift both pictures against each other, and where they fit best, you get a maximum, and where you have the maximum, you can assume that that's the position of the specimen at that time. And then when you have the position, you can shift it back. It's very, very easy. So, next part, the DFT login method. We have a sinusoidal course, our force, so we assume that we have a sinusoidal reaction. And our intention was that we take a DFT and get a bunch of sinusoidal parts that we can put together as our fit. And this is our fit, for example, and this fit consists of several parts. There's one the average part, there is this thermoelastic part with the loading frequency, and then there is the dissipative part 2F with a double loading frequency. And the next part we have to measure some things out. These are the amplitudes. First, the average temperature of the specimen, then the thermoelastic amplitude, the dissipative amplitude, and then there's only missing the phases. We do the same. We took the force, measure the phase, and also the same with the 2F amplitude. So, what are our results? If we don't do any motion compensation, we have the problem that sometimes the picture is not symmetric. Normally, we assume that we have a symmetric stress field in front of the crack tip. This is our specimen with a notch, and we have a crack with 5 millimeters, and this specimen is stressed with 8 kilonewton. And when we do motion compensation, the symmetric is fully restored. All double pictures, it's not seen on the notch, are gone, and even on places where the emissivity changes between paint and not painted surface is restored. If you see, compare it with this. Although on the double amplitude, double frequency D amplitude, we have the same reaction. All double images are gone. It's more sharp. We're even able to eliminate a bit the structure of the paint. So, to look more in detail, we took a vertical profile through the hottest place on the specimen, and we'll see here's a crack, this is above the crack, and this is below the crack, and then we have a shifting caused by the movement of the specimen, because during compression we have a heating up and the specimen is pushed to above, so we have higher temperature, and when the specimen is stressed, gets tension, it's elongated to the ground, and the temperature is lower. This is very, very dominant at high stress intensities on the specimen. And I'll call it, for understanding, the shifting effect. The next part is looking at the temperature spreading at the ligament. There I look at the average temperature at a lower stress intensity factor, and you'll see that the maximum and minimum value in this area is crucially infected by the motion compensation. They are merged together so that you get a smaller scatter of average temperatures in the ligament. This is very crucial for stress measuring. I will show you in the conclusion. So, let's have a look on the crack path. When we look at the crack path, we see the phase of the E amplitude, and you see where no crack is, it's like we expect, we have no shifting. Then we get a shifting over here. In 2004, Dia said that it's a place where the adiabatic conditions is lost, and so we assume that there must be the crack tip. And we also see a phase shift, phase shift between the area where the crack is and behind the crack of nearly 180 degrees, or of P. So that the area in the crack is in counter shift to the area behind it. So we assume that the crack must be maybe there. So have a look at our result from the potential drop, but the potential drop says there is a crack tip. And if we compare this with our E amplitude, we see the shifting effect that is compensated via motion compensation, and we see that the crack tip matches with the hottest, or the place where the highest amplitude of the E mode exists. So sum up everything, we have the motion compensation is necessary in all experiments, because we have the shifting effect that is dominant at high stress intensity factors. We have the merging effect that's dominant at low stress intensities, and both together influences our stress field in front of the crack. So it is crucial to, if you want to measure stress intensity factors, if you want to measure stress fields, you have to do motion compensation. and it allows a better location of the crack tip, but we already not know where the crack tip really is, because we can't define a criteria, a thermographic criteria based on thermographic images to define the crack tip. But I think we can solve that problem in the future. We also can connect effects to tension and compression, because we have the phase value, and we are seeing that the phase value is also influenced by motion compensation. And one further problem we have to deal in future is we have more frequencies than we expect. There is the average part, the thermoelastic part, the 2F part, and then we have two significant parts with higher frequencies, and we are not knowing how to deal with it. If it is only a mathematical effect, artifact from DFT, or it is a real mechanical effect, we cannot explain it. So, thank you for your attention, and maybe you have some questions.